Hello, my name is Greg Cox, and this is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. Everyone knows that we remember stuff that just happened better than stuff from further in the past. Even better, this recency effect is easily observed in memory experiments. For example, if you study a list of words and then are shown a test word from that list, you will tend to respond more quickly and with fewer errors if the test word was from the end of that list. Numerous explanations have been proposed for this recency effect, including the decay of memory strength over time, interference from subsequent items, a short-term store, priming from residual activation of features from recent events, a backward scan of memory, and the shift over time of the contextual cues used to probe memory. Now, something else we all know is that we have a memory advantage for the very beginning of a sequence of events. Primacy is typically attributed to different types of mechanisms than those used to explain recency. For example, the SAM model explains primacy as resulting from the fact that earlier items don't have to compete with other items for rehearsal time. Similarly, primacy has been explained in terms of temporal distinctiveness. Finally, other models assume that primacy results from elevated attention to items at the beginning of a sequence. The point is that, with the possible exception of temporal distinctiveness, the categories of explanation offered for primacy are quite different from those offered to explain recency. And yet these both seem to be fundamental features of how memory operates. Furthermore, the relative sizes of these effects can vary, including as a function of participant expectation, suggesting that whatever causes them, they are under some degree of participant control. What I'm going to talk about today is a model that jointly explains primacy and recency, and how they're balanced in terms of a shared set of underlying memory mechanisms. Now, for this proposal, I'm indebted to several individuals, including Gordon Logan, Amy Chris, and Rich Schifrin, although I should emphasize that while I have stolen their good ideas, any flaws or oversights are entirely my fault. From these three folks, I've gathered three main ingredients to brew an explanation for primacy and recency. The first is the idea of a temporal context that consists of features of recent items and which can be used to represent order information in memory. The second is a mechanism for encoding and recognizing associations between items. And the third ingredient is a dynamic approach to recognition based on feature sampling that jointly accounts for recognition accuracy and response time. I'll first describe these three ingredients in the reverse order in which I just introduced them, as I gradually mix them up into an integrative account of primacy and recency. I'll give some examples illustrating that this model provides a good fit to primacy and recency effects in recognition memory as well as to related phenomena. And finally, I'll discuss the relationship between this explanation and broader aspects of memory theory, focusing on its potential value for leading to more integrative theories of event memory. To begin, let me first describe the dynamic approach to recognition. Consider studying a list of items, like words. This results in the formation of memory traces, which contain features of both the items that you encountered and of the context in which they were experienced. Context here refers to what we might call environmental context, that is, the general time, location, and task demands that are expected to be relatively stable within an experiment. This is distinct from the temporal context I just mentioned, but we'll return to temporal context in a few minutes. The item features, on the other hand, represent perceptual and semantic aspects of the items encountered, essentially the content of the event of encountering that item. Storage of events as memory traces is not perfect. The traces might be missing features, as represented by the open circles here, or they feature stored might themselves be incorrect. Now, imagine that you're presented with a test item and asked whether it was present on the list that you just studied. To do this recognition memory task, you build up a representation, which we call a probe, and compare the features in that probe in parallel to those in the memory traces. This will tend to activate traces if they contain matching features with the probe, and deactivate traces if they contain mismatching features. Initially, the probe contains only environmental context features, since those are persistent, as I described, and as a result, traces from the list will tend to be active, whereas those from other prior contexts will tend to be deactivated. The average activation across memory traces that are above a minimal threshold constitutes your memory strength at any given moment in time. Shortly after the test item is presented, features of that item gradually begin to get accumulated into the probe from both perception and knowledge access. As this happens, traces that contain matching features will tend to increase in activation, while traces that contain mismatching features will tend to lose activation. Eventually, if the test item was on the list, memory strength will tend to have increased from its initial context-based level. On the other hand, if the test item was a foil that wasn't on the list, memory strength will tend to decrease from its initial context-based level. You make a decision by tracking these accumulated changes in memory strength from its initial point, and if that accumulated change reaches an upper boundary, you'll say, yes, I think that was on the list, and if the accumulated change reaches a lower boundary, you say no. Notice that these boundaries start far apart and then grow together over time as the probe gets more complete and saturated with features, reflecting the idea that sometimes the first few features provide rapid diagnostic evidence, while at other times individual features may only provide weak evidence, and so you need to sample a whole lot of them in order to make an educated guess. On different trials, the trajectory of memory strength will differ, owing to differences in the memory traces and in the order and timing of the features that are sampled into the probe, such that over trials, the model predicts an entire distribution of response times as well as the probability of making either a yes or no response to a particular type of item. Recently, Amy, Chris, and I extended this model to account for associations between items. Let's imagine that instead of a sequence of single items, they were in fact studied in pairs, like so. In this case, in addition to item and context features, memory traces also contain associative features. Associative features represent conjunctions between item features and are shared between the traces of items that were studied at the same time. When tested with a pair of items, you build up a representation of each item in working memory, just like as we saw with single item recognition, but in addition, you form associative features between the items in the test pair, just like you did when you studied them together. Because associative features represent conjunctions of item features, encountering the same or similar items, again, results in the encoding of the same or similar associative features in the probe. This gives a boost when the associative features formed in the probe match those that had been formed during study, letting you distinguish between intact pairs that had been studied together versus rearranged pairs that had been studied separately. Now, the final ingredient. Let's go back to the case where the items are studied individually in a sequence. At this point, I'm going to switch to visualizing the content of memory traces by using these labeled boxes, with the understanding that under the hood, these boxes actually represent collections of error-prone features like we saw before. Now, imagine that, as you're studying the list, you maintain a running history of the features of previous items. This history is a temporal context, like in Howard and Kahana's temporal context model and in Gordon Logan's recent context retrieval and updating model. When you encounter a new item, features from the previous item replace some proportion of the features that had previously been in the temporal context, meaning it primarily contains features from the most recent item and somewhat less from older items. Although the idea of a temporal context of this kind is hardly new, going back to Estes, we do get something novel if we assume that we store these temporal contexts as traces in memory. In other words, each study trial leads to the formation of two traces, one for the item and one for its temporal context. And just like when you encounter two items at the same time, the traces of items and their temporal contexts are bound together by shared associative features. It is this representation that allows us to simultaneously explain primacy and recency, using the same mechanisms that previously accounted for item recognition and associative recognition. Primacy arises because traces of the item contexts will tend to overrepresent early items, making it easier to find matching features for items that had occurred at the very beginning of the list. how does recency arise? Well, even though there's only one test item at a time, we assume that just like the temporal context is present at study, it's also present at test. As a result, when you're encoding the probe, you'll also encode associative features that represent the association between the test item and the temporal context at the time of test. Even though this temporal context doesn't exactly match that of the last study trial, it's very similar. And because similar item features lead to similar associative features, this will give an extra set of features that match for recent items. So to summarize, the storage of temporal contexts as traces in memory leads to primacy, because temporal contexts will tend to contain more features from earlier items than later items. The encoding of associative features between items and temporal contexts leads to recency, because the temporal context at test will tend to be more similar to that of later items. The relative balance of primacy and recency is partially under participant control, because the participant can choose to give more or less attention to the temporal context during study, and the participant can choose to give more or less attention to those associative features at test. For example, these results from McElry and Dozier, which demonstrate a mixture of primacy and recency, are accounted for by the model by assuming relatively strong encoding of temporal contexts. Represented in the model is the probability of storing a temporal context feature in its respective trace. This is in contrast to these results from Nozovsky et al., which don't demonstrate primacy, and accordingly, the probability of storing temporal context features, according to the model, is considerably lower. Now, the model also counts for a recognition advantage when items are tested in the same or similar order as they were studied. For example, these results from Schwartz et al. Show that when the previous test item had been studied closely before or closely after the current test item, there is a higher probability of recognizing the current test item. Moreover, there is a slight asymmetry whereby testing in the same order confers a larger advantage than in the reverse order. For the same reason that the model predicts recency effects, it predicts precisely this form of advantage. The test context is more similar to the study context, such that when the test item is associated to that test context, the resulting associative features better match those that had been formed during study. The proposal I put forth today jointly explains primacy and recency in terms of the same set of common memory mechanisms. Of course, it's entirely possible that the other mechanisms, like those I described at the beginning, could still be operating. The point is just that we don't need different kinds of mechanisms to explain these fundamental memory phenomena. Core to my proposal is the idea of associating items with temporal contexts, which is hardly a new idea, but while it has been used a lot in free recall and memory for serial order, it is yet to be fully explored in theories of recognition. By doing so, we're essentially integrating memory dynamics across timescales, between trials, described by temporal context, and within trials, as described by feature sampling. In addition, there's some novel aspects to this use of temporal context. First, as we've seen, the temporal contexts themselves are also stored as their own memory traces, which then explains primacy. Second, while most temporal context-based explanations of recency assume that you directly compare the test item to the temporal context, my proposal says that instead, you build an association and check if that matches the contents of memory. Of course, there's no reason why one couldn't compare a test item directly to the temporal context. It's just that in that case, the temporal context would basically be a kind of fuzzy short-term store. One potential advantage of using associative features rather than a direct comparison between a test item and temporal context is that it makes clear how the same mechanisms that bind items together can also bind items with their temporal contexts. Indeed, pure pairwise association would arise in the case where the entire temporal context got replaced on each trial. And because both the temporal context and associative features are sensitive to similarity, this approach might be a general way to think about sequential effects in memory that involve those forms of similarity. And finally, if this proposal has any value at all, I think it's largely in illustrating the value of modeling for finding integrative explanations, especially in memory research, which tends to be dominated by a focus on punctate effects. Now, to put it another way, maybe what this is all saying is that we really can all just get along. Thank you very much for your time.